If you ask me to name one of my favorite subjects, I will definitely put EMT at the top of the list. The way this subject plays with your intuition is mind-blowing. This subject involves complex mathematics and proper reasoning. Without solid reasoning, you cannot come to a conclusion and may stuck to a problem forever. In this session, I would like to discuss such a problem. I would like to discuss the inconsistency that arises when you try to calculate the energy of a point charge distribution and the energy of a continuous charge distribution. But before we look into this inconsistency, let us first derive the energy of a point charge distribution and later the energy of a continuous charge distribution. If I ask you what is the total amount of work required in order to assemble 4 charges at a place, you will definitely going to use this formula, which say work done equals to charge times the potential. As you all know that potential is given by this expression. You will assemble the 4 charges one by one. First you will bring Q1, for which you have to do 0 work because Q1 does not have to fight any field. Next you will bring Q2. This time you have to do the work because Q2 will have to fight the field created by Q1, and as a result the work done is equal to Q2 times the potential created by Q1. Next you bring the third charge. You have to do more work. This time the work required is Q3 times the potential due to Q1 plus the potential due to Q2. And finally, when you bring the fourth charge, you have to do even more work. This time it is Q4 times the electric potential due to Q1 plus the electric potential due to Q2 plus the electric potential due to Q3. And finally, the total work will be equals to W1 plus W2 plus W3 plus W4. In general, if you want to calculate the work required in order to assemble n number of charges, you have to take product of each pair of charges, divide by their separation distance and add it up all. And in compact form, the formula will look like this. You should not count the same pair twice. There is another way of rewriting this formula. This time you intentionally count each pair twice and then divide by 2. But what we gain after modifying this formula? Now in this form, the answer plainly does not depend on the order in which you assemble the charges, since each pair occur in the sum. If Q1, Q2 occur in the sum, then definitely Q2 and Q1 also appear in the sum. And in this way you see the order doesn't matter. Next, you pull out the factor Qi. The term in this parenthesis is the potential at point R1 due to all other charges. And finally, we arrived at the formula for calculating the work done required in assembling n number of charges. It's also the same amount of work you will get back if you dismantle the system. This work done represents the stored energy in the configuration, which is also known as potential energy. Now we will derive the energy of a continuous charge distribution. The energy of a continuous charge distribution is given by this expression. This expression looks very similar to the expression that we have derived previously in case of point charge distribution. In this expression, the summation term is replaced by integration and Q is replaced by volume charge density. Now instead of summation, we have to integrate it over a volume, and the work done expression finally look like this. What can we write the work done in terms of field, specifically in terms of electric field? Yes, we can write it. From Gauss law, we know that the volume charge density is equals to epsilon naught times the divergence of electric field. So W will become epsilon naught by 2 integration divergence of E times V dV. Please remember that here V is potential and not volume. We have to solve this integration. Now this integration can only be solved by using by parts. If you don't know how to apply by parts in vector calculus, you can go through this derivation. Now just look at this formula. By parts license us to transfer the derivative from A to F at the cost of minus sign and a boundary term. If you look at the left term of this equation and compare it with the right side of this equation, you will come to know that instead of A we have E, and instead of F we have V. Therefore the work done will equals to epsilon naught times 2 minus integration E dot the gradient of V into dV plus the surface integral of V E dot dA. So replacing the gradient of V from this equation and substituting the value, that is minus E, we have work done equals to epsilon naught by 2 integration E square dV plus surface integration of VE dot dA. What volume is this we are integrating over? It should be clear that we should integrate over the region where the charge is located, but actually any larger volume would do just as well. The extra territory we throw in will contribute nothing to the integral, since rho will be 0 out there. What happens here as we enlarge the volume beyond the minimum necessary to trap all the charge? Well, the integral of E square can only increase because integrate being positive. As a result, the surface integral must decrease to leave the sum intact. In fact, at large distances from the charge, E goes like 1 upon r square, V goes like 1 upon r. Therefore, this product will go like 1 upon r cube. But the surface area grows like r square. Then the overall integral goes down like 1 upon r. As I have told you, the sum will remain intact, which means that if you increase the contribution from this term, then the contribution from this term will go down, and when you increase the contribution from this term, then the contribution from this term will go down. We want that the contribution from this term to become 0. So what we do, we integrate it over the whole space. As this term was going down like 1 upon r, and now we are integrating over whole space, that means the radius is infinity, the contribution from this term will become 0, and finally we arrived at our final expression of work done in terms of electric field. And now comes the real twist. Now we will discuss the inconsistency that occur between the two expressions of work done that we have derived. The first expression that we have derived is for point charges, and using the point charges we have derived the expression for a continuous charge distribution. Now, according to this formula, the energy of a stationary charge distribution will be always positive because its integrand is always positive. On the other hand, the energy of a stationary charge distribution may be positive or negative. It is negative when we calculate the energy of two equal and opposite charges. So, which equation is right and which equation is wrong? How one can guess? In fact, this expression is derived from this expression. So, which one is correct or which one is not correct? Well, the answer is that both are correct, but they speak to slight different question. This equation does not take into account the work necessary to make the point charge in the first place. We started with the point charge and simply found out the work required to bring them together. In fact, this equation is more complete in the sense that it tells you the total energy stored in a charge configuration. Whenever we deal with point charges, we prefer to use this equation because this equation leaves out the portion of the total energy that is contributed to the fabrication of the point charges themselves. In practice, after all, the point charges are given to us ready-made. All we do is to move them around. Since we did not put them together and we cannot take them apart, it is immaterial how much work the process would involve. Second dazzling question is, where is the energy stored? Whether the energy is stored in the field or it is stored in the charge configuration. If you speak in the context of radiation theory, then the energy is stored in the field with the energy density given by this formula. But when you speak in terms of electrostatic, the energy is stored in the charge The third question that I would like to address is, does this electrostatic energy obey superposition principle? And the answer is no, it does not obey the superposition principle, because the electrostatic energy is quadratic in the field. As a result of this, the energy of a compound system is not the sum of the energy of its parts considered separately. There are also cross terms, and in this way the superposition theorem is not obeyed. In conclusion, I would like to remark that if you dive deep into the subject of electromagnetic theory, you can find such type of inconsistency at every stage, which is worth spending time and finding why it occurred and how it was solved.